Hi, my name is Mei Collins and I'm an intern at the Periodontal Lab. So, for billions of years, nature has perfected certain processes that occur in organisms which require not that much energy and are extremely efficient. However, when humans try to replicate these processes, it often doesn't turn out so well and requires large amounts of energy and therefore work and waste. In the Periodontal Lab, we're looking at a certain reaction called oxidation. And within organisms, of course, this occurs without a lot of energy used. But a certain chemistry called Fenton chemistry has tried to replicate it, and it has resulted in a lot of waste, a lot of toxic byproducts, and just not a successful outcome overall. However, we've managed to make a certain complex that replicates this without all that extra waste or dangerous byproducts. So this is replicating a metalloprotein, which is found in organic organisms, and it is very useful it would be very useful in industrial applications because it would greatly reduce that energy and waste. So for my project specifically, the lab overall is working on reducing the decomposition of this molecule because although it works, it can still break down over time, and of course this is not ideal. So there are two different methods that the lab uses to try to prevent the molecule from breaking down. The first one is creating a resin surface onto which the molecule can adhere to, and this will allow the molecules to stop attaching to each other and therefore breaking down. And it also allows something called flow chemistry to occur, in which the reactants move over the resin surface and move about through their synthetic processes. This, for example, would be very useful in a pharmaceutical application in which they're trying to synthesize products. The second way that we try to reduce the decomposition of these molecules is by creating a ligand that attaches to the complex and sort of protects it, just like how a protein would protect its active sites. So, in my project specifically, I'm focusing on the latter option, in which creating a ligand and examining different properties of it will affect its reactivity. So I accomplished two objectives within my project. The first was that I observed the effects of adding a certain group called a ketone onto the baseline ligand that we have, called N2O1. So adding this ketone, I added an isopropyl group, would allow us to have a greater horizon for creating a lot of different molecules as well, with a whole bunch of different applications in terms of reactivity and stability. The second objective I obtained was I added another group called an adamantyl group. This group is very large in comparison to the rest of the molecule, and it allows it to be more stable and increase its solubility. This is very important for a bunch of different applications as well, and also opens the horizons to new creations of the ligand. So overall, these different synthetic developments provide further elaboration and modification of the ligand. And within this project, I've learned a lot of different chemical pursuits and processes that are essential to working in the lab. For example, I've learned something called TLC, which is thin layer chromatography, as well as column chromatography, which used in conjunction are really important and essential to purifying the product that you're trying to find and isolating it. I've also learned a lot about analysis of these molecules that we make, including NMRs and spectroscopy, which are all very essential in the lab. I've had such a great time.